Yeah, can you share the screen? Remember you
Yeah.
must share the sound. Yeah.
Yeah. Can you see it?
Yes, very good. Please.
Okay. Good morning, everyone. I'm Mingguo Zhao from the Robot Control Laboratory in the Tsinghua University. I would like to
Well,
thank Professor Zhang for her invitation. As we know, sorry, as we know, humanoid robots and embodied intelligence are gradually interesting, and they may bring out changes to our lives in the future. I am honored to share here some of the progress of our laboratory in humanoid robots and embodied intelligence in ICANX talks. My presentation is titled as Kicking Like Humans, like the embodied intelligence of humanoid robots. In this presentation, I will discuss the development of humanoid robots with embodied intelligence in the context of humanoid robots. I have been engaged in RoboCup for over 20 years. The main research is that the main reason is that I believe challenge like RoboCup can promote the development of embodied intelligence and ultimately uh, generate significant social applications. So I have some thinking and some results can share with you. My presentation is composed by the following four parts. First, I would like to take a moment to review the RoboCup and introduce its relationship with other AI challenges. You know, in 1997 stands an important year in the history of artificial intelligence and robotics. In May of this year, the IBM Deep Blue computer defeated the world chess champion. A standard challenge is completed. This is a significant milestone after 40 years of challenge in the field of artificial intelligence. So once a challenge is finished, people began to consider what the next challenge will be. So the concept of using robots to play soccer games was introduced as earlier as 1993. In 1996, the RoboCup Federal was established. Then, with the goal of having a full autonomous humanoid robots football team defeated the World Cup champion and the FIFA rules by the year around 2050. So the first World RoboCup took place in 1997 at the IGCAI conference as a joint activities, just following the Deep Blue's victory. So this event was supported by Sony, IBM, and Microsoft, also the big companies at that time. Uh, why the Robert Soccer game was chosen? Scholars have already made various technical comparisons between chess and robot soccer. I list five aspects. Uh, the five aspects listed here are all very important and easy to be understood. For example, the difference between static and dynamic environments is very important to clarify the chess and the robot soccer is quite different. And for the control aspect, the centralized and the distributed control method also have a great difference. Uh, this is why we choose robot soccer, yeah, as a next challenge. Uh, this comparison highlights that the technologies needed for the job sector align closely with what is currently defined as embodied intelligence in today. So we think it's time for the RoboCup for to engage in the embodied intelligence today. So I think everyone needs to draw attention here. IBM has built an artificial intelligence architecture through the achievement of Deep Blue, surpassing humans in the field of chess. Then they applied it to its Watson system. You can see at the right upper pictures, using the IBM using Watson to solve medical care problems of the human society. But the IBM's Watson system did not ultimately succeed for various reasons. However, using the challenge to help us solving major problems of the society is still ongoing. This is the story of how the famous AlphaGo defeated the humans in 2016. It is followed by AlphaFold, remarkable success in the field of genetic engineering. And finally, they earned the Nobel Prize in last year. Although the IBM failed to succeed, DeepMind succeed instead in a different area. I think this is an important lesson for the RoboCup society, also for all of us, because a new technology cannot achieve commercial or practical success overnight. It requires a milestone to first validate the technology and then increase investments and also in its application. So in this aspect, we will ask, what will the RoboCup bring to the world if we succeed in obtaining a certain technology in the RoboCup? Which major problem will be solved? In other words, RoboCup is no doubt a milestone for humanoid robots and embodied intelligence. But it is necessary to determine what is its potential future applications might be. So I choose some choice. Maybe our society is an aging society, and we have a lot of other problems about on the labor force shortage or some domestic service works. So all of them are potential significant social demands. So we can use the techniques we gain from in the RoboCup to serve us in the future. So inspired by IBM and DeepMind, the development of RoboCup should pay attention to the following points. First, it should be able to solve major social problems in the future. And then second, embodied intelligence is an important means to achieve this goal. So I suggest the roadmap for RoboCup participants may be we can get like the embodied intelligence should be realized in RoboCup first, and then apply them to more complex real embodied scenarios. So as far as I know, beyond the current RoboCup, some work is underway. So let me introduce two examples. First, an article published by DeepMind in Science Robotics in last year discusses how they use reinforcement learning to enable small humanoid robots to autonomously kick a ball and get up by an end-to-end approach. You can see the video on the bottom right. Well, they currently will not be competitive in the RoboCup Humanoid League, but all the things they do were executed through reinforcement learning, making this approach noteworthy. So I think RoboCup Humanoid League will increasingly utilize this technology in the future. Almost all the team will using these technologies. So I have engaged in these techniques. Second, I will like to introduce two ongoing projects from the Booster Robotics. They are developing a standard humanoid platform, aiming to enable more people to build upon this platform to develop various technologies related to humanoid robots and embodied intelligence. We can see the video have a site. This platform is like a kid-sized human child. It can walk and get up and have the kick and find the ball and find the goal. Yes. To achieve this goal, the robots must be robust and intelligent enough. That is, it must be capable of processing sufficient control skills, working in a natural environment, and collaborate with the other team members. So it must be full autonomous, have skilled, and work in natural environments and can do some teamworks. So they also developed we call the AI assistant teleoperating football game. This means before the full autonomous cycle robot game, we developed this AI assistant game. We can see this video, yeah. So you can see some human operator behind the goal. They're using the remote controller to control the robots, but the robots have autonomously functions. They're using their camera to recognize the ball, recognize the environment, and they can kick the ball by themselves. So we merge the human operator and the AI system. So we call this game is AI assistant.
恭喜我们的 Stark 队赢得了最终的冠军。
So humans in this game remotely control the high-level decisions, such as the robot's positioning, running to a right position, and the team cooperation. And while the AI completed the techniques such as walking, dribbling, and kicking, and get up after falling down. So this AI assistant system merged the advantage of both humans and the robots. By now, it's a successful way to separate the robots. Yeah. The first achievement of this game is they achieved a 3-v3 match for adult-sized humanoid robots without a human handler. I will explain what is the meaning of a human handler in RoboCup later. The second part of this report, I will review the Humanoid League competitions in last year. That means RoboCup 2024. Yeah, you can see this picture. Yeah, also this is a video. This video is a segment of idle size competition in the Humanoid League. We see the video here first. In the game, there have 2 teams. Each team have 2 robot players. It should be noted that the handler behind the robots only get involved in rescue operations when the robots breaks down, or the falling down, or has something broken, or like this. However, this has seriously affected the competition. This issue must be addressed first. So autonomy refers to a system's ability to operate independently without human interrupts. Full autonomy involves multi-components. In summary, full autonomy means the system can sense, decide, act, cooperate, and complete entirely on its own. So for the RoboCup game, all the robots must satisfy the full autonomous system. So this means they must have some locomotion subsystem, sensing subsystem, decision subsystem. And so the robot must be have some cooperation functions because they will cooperate between the team member and have competition with the opponent teams. The locomotion means the system moves to take actions based on his decision. Sensing means the system perceives its environment using sensors. Here, the robots can only using the camera like humans to sense the environments. So they also have some decision systems to decision to make a right decision for itself behavior and the team behavior, and make some defines to compete with other teams. Yeah. So this slide will show some skills for a single humanoid robots in the soccer game. This is a video from the champion team from the UCLA last year. So in the last year, robots also demonstrating a range of essential skills like walking, you can see in the video, localization and obstacle avoidance, ball control, and the team strategy. These skills are vital for competing successfully. So in this slide, I will show some 4 special scenarios. The first show in the upper left video is this is the case of this is called free kick. You can see there have already been excellent free kicks. Both the offensive and defensive players can achieve position and demonstrate excellent strategies. In the upper right video, you can see there will be face-to-face collisions among the robots, and the competition is a very high competitive game. Moreover, the uncertainty is very strong during the game. We show this in the lower left video. For the white robots, it's almost a goal, but with some uncertainty, the right robots get this robot lose his opportunity due to some uncertainty, and another team gets a goal in here. So at the lower right video, the blue robots they gain opportunities because the 2 right robots have already blocked the attacking routes, but suddenly they left. Thus, create a very good space for the blue robbers. Yeah. All this has complexity and uncertainty have raised the higher requirements for the game. So previous technologies seems unable to meet these requirements. So we must using some new technologies. Yeah. In this video, I will show some aspects of stability in the real applications. In this video, stability is a great significance for competition. Even the robbers, the red one, is from the champion team, will face multi-falls during a match. So they need to be extremely reliable for complete a game. So we need the robber to be crash-proof, impact-proof, capable of push or fall recovery from the falling down. Moreover, some stability occurs not for the physical parts of the robbers, also for the algorithms parts of the robbers. You can see this video. It should be very easy for this robber to get a goal, as you can see here. To lose the chance of goal have about five times. Well, I guess their shadow of the goal block the robbers have a right sensing the sensing of the ball. So when he see the ball, he go back, and when he approaching the ball, lose the ball. So he go back to find where is the ball. So for the robbers, ability to adaptability to the environment is very important. They can come from the vision, or maybe in the future for some audios should be very stable to cope with the competition. Even the champion team of Parisian, like this white robbers, may encounter difficulties in the game. Yeah. In the third part, I will briefly introduce some work of our team, Tsinghua Hephaestus RoboCup team. Our team is established in 2004. We participated in the RoboCup for almost 20 years. We have always hoped to make some contribution to the development of RoboCup. Yeah. We have developed 7 generations of robots from 2006 to 2024. Yeah. This is the first, and this is the second one, and the third we call the stepper and a dribbler and a walker. This walker is cooperated with the Robert company outside Tsinghua University. Then the last one is from our previous team member. They found a robot company called Booster Robotics. Drawing on the stability principle of passive dynamic walking, we design a method that can generate the same stable periodic motion on the flat ground with the small actuations, which we called virtuous walking. We can get the robbers to work very simple and very efficient. This robot was built 2007 or 2008. So we get the runner-up of last year in the Suzhou of RoboCup Humanoid League Tencite in Tencite. Another part of our work is focused on whole body locomotion. In order to better develop the dynamics of humanoid robots, we have developed a set of whole body control techniques based on optimization methods. So like the diagram on the left, we have a part of whole body control. This is a multitask with multi-constraints. And for the humanoid robots, we must control the body to upright and control the force on the foot and control the gesture of the hand. So in order to have a good command of this body parts, we're using a multi-predictive control. Also optimal optimization problem. So this system include MPC, this means model predictive control, and a whole body control parts. These two parts cooperate with the state estimator, can work this robot very functionally, like this one. This robots can be called Mario. It's a 3D like the robots. It can walk on different terrains, also with some disturbance from the outside. These robots can determine what the foot the robot can have the footprint. Another demonstration is for the shake hands with the robots. So if the hands moves slightly, so the robot will adapt the human to with his all the joint of the whole body. So we're using this, we call this whole body control. Also, the robots can adapt to the force, the disturbance from the ground. With at the same time, we have a disturbance with on the body. So only the optimization method can solve this problem in the same time. After the competition last year, we began to research and applying reinforcement learning techniques. We call the RL reinforcement learning and sim-to-real techniques. We have already solved the problem of locomotion with reinforcement learning rely only on proprioception. We're using two parts. One part at the left picture is we train the model in the simulation environment, and we got a policy. And then we put the policy on a virtual and real merged simulation system to verify the algorithm can be run on computation systems. Then we distribute the system to the real robots. The first, we can get the robots to have a push recovery function. So these robots have policy to deal with what's the walking, deal with the what's the next motion of the each joint, and they have when the outside have a disturbance, how to put their legs. So we are addressing the reinforcement learning problem such as dribbling and kicking and defending. These problems are within the embodied intelligence domain. I will emphasize in this report. This is our team members in the last year. In the next part, we have some discussion on the embodied intelligence. Over the past 6 months, our team attempts have provided us with a valuable insight into the embodied intelligence of humanoid robots. So I will give a brief introduction to these topics in the following sections. This video showcases our participations in the robots obstacle avoidance racing at the Humanoids 2024. At this conference, the robots must walk and have the ability to the obstacle avoidance and then have some operation. But you can see this video. This robot is controlled by a remote controller, and then he has some skills to open the door. Very not skillful. So although this robot's locomotion is driven by reinforcement learning, it can walk on uneven terrain and handle external disturbance. However, remote control is still required to obstacle avoiding. Also, some operation with hand must be controlled with the remote controller. So as a result, these robots demonstrate limited adaptability to their environment and have insufficient abilities to complete tasks independently. So, which means they do not represent, I call a standard embodied intelligence. This means these robots have the locomotion with reinforcement learning. It belongs to the domain of embodied intelligence, but it's not a standard embodied intelligence. We see this video. As mentioned earlier, we hope the robots can autonomously stand up after falling. So we adopt a two-stage curriculum learning approach and completed a solution that enables the robots to stand up quickly in various postures. So we see this result.
The robot successfully recovers from various fall scenarios, achieving a stable standing posture from different initial states. Our policy enables the robot to recover autonomously in complex environments, including slopes, obstacles, and outdoor terrains like gravel and grass. The robot compensates for additional 5 kilograms weight and recovers from falls, while external disturbances such as pushes and ball impacts trigger a controlled sitting posture before executing a high dynamic recovery. The policy integrates push and fall recovery, allowing the robot to maintain balance with ankle and hip strategies, take recovery steps for stronger pushes, or adopt a safe impact posture before standing up. After recovering from a fall, the robot transitions seamlessly to locomotion mode, ensuring smooth and efficient movement.
This technology was applied in the Booster Prime League, in which the handler behind the robbers was removed. I think this great improved for the robot soccer system. Although this is very helpful for the competition, but this is the same motion control problem as the previous examples. As you know, for the reinforced learning, we have a pipeline to train the robots. But for some problem, like the falling, when the robot is falling, we must get up. We call the fall recovery. For the fall recovery, we cannot have this function be solved by a simple reinforced learning pipeline. So we're using a two-stage curriculum to learning approach. The first stage, we only train the robots with only at the two-dimensional problem. And we do not constrain the robots as the real robots. We lose the constraints. At the second stage, we have a hard constraint and also have a three-dimensional environment give to the robots, make the robots to learn how to find a strategy to get up. So even this is a very complex pipeline for the robots to have a reinforced learning. But from the type of his function, it's only using the internal sensors, let's say gyro and the torque of each joint. So it's also not a standard embodied intelligence problems. It's all locomotion only. So we think we can do some better embodied intelligence problems for the soccer game. So this video demonstrates our robots have the ability to identify and tracking the ball through using his vision systems. This video is taken from the aerospace.
Okay, we are now seeing that the robots are chasing the ball autonomously.
The robots can find the ball and track the ball, and also have the decision making to
Okay, we are seeing
approaching
volunteers
it.
from the audience playing together with the robot.
So you can see the robots can adapt to the environment.
A very shy kick from the
It's
audience.
three people not how the define it.
Robot
Find
is
the
trying to get to the
action.
ball, but it missed the ball and they lost the ball now. So what to build the up, they found the ball again.
So this robot utilizes his vision, using his decision making, planning, and locomotion to get intelligent behavior. However, its behavior is very simple. Its behavior is based on a strategy written by humans. It's very simple strategy. So its capability are relatively limited. So we want using reinforcement learning or imitation learning techniques and to enable the robot to achieve vision to action capabilities, which has more adaptability and versatility. So recently, and this way, we have achieved some preliminary results. So we called this also embodied intelligence. We called vision from vision to walk or from vision to kick. In the simulation, we randomly generate many balls and goals on a soccer playground, also with a field with the goal and with some other robots, to let our robots to explore how to achieve a goal. So we initially realized the end-to-end and end-to-end kicking function by constructing the word model. The word model means the robots can have a model about the environment. He can know where is the ball, where the probability of the ball, where is the goal, and the probability of the goal, and where is the obstacle, and also the probability of the obstacle. So they can, based on the environment model, have a right decision, also using a network So we can see the results.
开了。哦哦。你要不穿个拖鞋吧？你找个鞋穿吧。这是不是左腿不太？
So the robots have many functions. It's using the vision to track the ball, to find the ball, and find the goal, and also he can determine which the routine for his to approaching the ball. So make a right kick. So this we call from vision to walk, from vision to kick, or from vision to pass planning. But we're only using single networks, as we call them MLP networks. So for the networks can have the ability to store the strategy of the robots for the walking, for the kicking together. But we do not know the detail of the robots, how the robots to get this function. We only have a network structure, also have some pipeline to train these networks. So all the policy is the robot himself get from the environment, from the reinforcement learning with the environment. The realization of this ability has strengthened our confidence in achieving an end-to-end cycled embodied intelligence only through learning technologies. Now we're only using the reinforcement learning. For the future, we want to get some imitation learning integrated in the system, because for the reinforcement learning, we can define the environment. We can define which we want the robot, which do not suggest the robot to do. But a lot of strategy of the human cycle player also have the strategy. The robots can learn from the human, but they do not know why we have this strategy. But the robot can learn from the actions of only the actions of the human. So by now, I think these two technologies, reinforcement learning and imitation learning, is a very foundation for the robots to have the intelligence. So I divided the second robots embodied intelligence to at last three parts. The first last only the locomotion. That means we only using the internal sensor to train the robots how the locomotion abilities. This is the first level, and the second level, like this example, we're using the vision of other outside sensors to train the robots have some ability, they have some skills. And then the third level, the robots can learn to cooperate with the other robots and can define the other teams. We call the teamwork level. So at the third level, we must using some LLM techniques to support these robots. Only for this embodied system cannot have this big ability only in the online system. So I will prospect the skill for one robots in the second game. So the first the robots we will further develop some technologies with reinforcement learning and imitation learning to achieve end-to-end walking, ball controlling skills, and the environment perception and the navigation, as well as the ability of locomotion of the fall recovery or the push recoveries. So these skills include omnidirectional walking. This means the rocket can walk forward, backwards, lateral, rotational. Also, the combine of these four parts we call the omnidirectional walking. Also, the football playing skills like dribbling and dribbling kick, volley kick, high kick. Also, kicking a moving ball. Also, we must perception the environments. We have localization and decision and navigation functions. But as I have already said, we only have one network. So this concept of the perception, localization, decision making is by our human, but for human robots, they do not clearly divided by this aspect. For the next part, the robot must have the push recovery or fall recoverability. So when this is an important aspect for the robots can play the game by themselves. So we will combine this high-level decision-making intelligence to make our humanoid robots more close to the ultimate goal of the RoboCup. So I will introduce some research work of our laboratory and also introduce some background of the RoboCup and what's the direction of RoboCup should to be. Thank you.